Hello everyone, this is Dr. Jan. In this video, we're going to talk about the column design equations, and I'm going to show you an example. Basically, what we're going to do is to find the design compressive strength VPN, and is governed by fractal buckling or local buckling. Most of the problems we are working on is about the global buckling problem. Usually it's not governed by local buckling, and in design we also want to make sure this column will not be governed by local buckling, because it will not be efficient material using wise. Okay, so in the Canvas course 3.1, we talk about the Euler's elastic buckling stress, Fe. Okay, so it's equal to pi square E over FL over R squared, and the KL over R is called slenderness ratio. It defines if the column is slender or not. Because we are not living in a perfect world, right? Because the column, especially the slender column, is always perfectly straight. So we have to count for the initial out of straightness. So typically, a 87.7% of out of straightness will be encountered. So we're gonna push the curve to your right a little bit. So there is no reduction. There is an 87.7% of reduction due to out of straightness. And so the Euler buckling equation defines the stress, the stress at failure for slender columns. Meanwhile, for the regular short columns, you apply a load on it, it fail at crushing, at yield stress. So the yield stress Fy of the material defines the failure stress for a short column. So theoretically, the two curves, the red curve and the blue curve, so the yield stress curve and the Euler elastic buckling curve intersect at a point, and this point theoretically defines the boundary of short column and slender column. Okay. However, that's just the theoretical thinking. Okay. And if you perform a lot of tests, you test on the different lengths of the columns and test as failure, the critical stress, you will find those data dots fall in a region like this. So you will see that the actual failure critical stress is much smaller than yield stress. Why this happens? Well, it is because the existence of residual stress. Residual stress is the stress remained in the steel member even when there's no load applied on it. So even the column leave it is free, there is still initial stresses exist in the columns, in the steel members. Why is that? Because it could occur during the uneven cooling and heating process, or it can take place anytime in the process of the steel manufacture. Anyway, residual stress just there. It can be ignored. So it will bring down your critical stress. So a curve, this black dotted curve is created to best fit in the testing data. And you will see there's a point of inflection in this curve. And that's the boundary between the inelastic and elastic failure. So if your slenderness ratio is less than 4.71 times square root of E over Fy, then we call it inelastic failure. Okay, and otherwise it's an elastic failure. And inelastic failure make better use of the material, right? And typically there we get the entire column buckling stress curve is made of two curves. The first portion of curve is we talk about due to the effect of the residual stress, and we create a curve best fitted the research data and develop this equation. Okay, so this equation defines the critical buckling stress for inelastic failure. And after that, and the critical elastic buckling stress is coherent with Euler buckling theory. So it's 0.877 times Fe. So the factor of 0.877 stands for account for the initial out of straightness. Okay, and this slide summarizes all the theory and the equations behind the column design. So first of all, the VPN for a column is equal to 0.9 times FCR times AE. So this is the equation E3-1 in your menu. And the first portion of the curve can be expressed with FCR equals to that. So that's equation E3-2 in the menu. And the elastic failure, the later portion of the curve, is in line with the Euler elastic stress, is 0.877 times Fe, as Fe is the Euler elastic buckling stress defined here. Okay, and you can find the equations from your menu. So let's look at your menu. Okay, so first of all, let's go back to your menu. I know some students still struggling with this thick menu. Oh, well, so if you look at the table of the content, you will get a overall idea, the overall content of this menu. So there are 17 parts in total, and all the equations, most of the theories and equations are included in part 16. It's called specifications and code. So we will find the equations in part 16. And for column design, all the tables are in part 4, design of compression members. So typically part 1 through part 15 provides the design aid, tables, graphs you're going to use for the design. So for example, we are doing the compression member design, so we're going to use the tables in part 4, and after that we're going to use part 3 a lot for beam design. Okay, so let's look at equations from part 16, specifications. And if you go to the page 16-1, you will see the table of content for part 16. Okay, and then next page, Okay, table of content, we'll get a brief idea of the structure of specifications. Compression member is in chapter E, so the first letter is the chapter letter. So chapter A, B, C, D, and E. So the compression member is in chapter E. Okay, and E section E1 gives you the phi factor. So for column design, phi factor is 0.9. And in page 16.1-35, give you the definition of effective length K. Okay, so you should be able to understand that from the canvas. And E3, section E3 gives you all the equations. So let's zoom in. Okay, so 10 to page from your hard copy, basic equation Pn equals FCR times Ag. Ag is cross-sectional area, and FCR is the critical stress. And the critical stress is determined based off its slenderness ratio. So LC is the effective length. So LC is equal to KL. And if it's less than that, so this is the first portion of the curve, right? This is equation for the first portion, and this is equation for the second portion. Okay, so and then you can link the menu to this graph. So this is a very important graph for this class. Okay, and you will know which equation you want to use to determine your FCR and then calculate your VPN. And typically, prior to solving VPN, you also want to look into the local buckling problems in the columns. And section local buckling is included in section B4. B4 means chapter 4. Okay, this is very interesting. The local buckling is described in chapter B. Okay, so find chapter B and section B4 to address the issue of local buckling. And the local buckling means the local failure, the local buckling in individual members. So typically the wide flange shapes are very thin, very slender. So we have very thin web and very thin flanges. So when the members have very thin element, it tends to buckle locally. Means prior to the global buckling, it probably will fail in the web like this, like the graph showing here, or you have very thin flanges, it probably will fail locally in the flanges. So those failures typically take place prior to the buckling we talk about in this graph. Okay, so we have to adjust the local. Typically, we will adjust the local buckling problem prior to other steps, and the local buckling is only related to width to thickness ratio. Width to thickness ratio is the ratio of the width of the element and is thickness of that element. So for example, for the flange, the width to thickness ratio is the width of the flange, BF, over the thickness. Okay, so thinking about the local buckling is only about the individual members. So when we check the local buckling for a wide flange, we are actually looking at this portion, right? So it's like a cantilever plate, the plate here. So the width to thickness ratio of this portion is BF over 2, right? So half of the width over the thickness, TF. And the width to thickness ratio of the web is the width of the web actually is the clear height h over the thickness h over tw. So you will find the value of the width to thickness ratio of the flange and the web from table 1-1. And you know that local buckling may reduce the column design strength. So when you design a column, we tend to avoid to local buckling shapes, okay, because it may reduce your capacity. Okay, so here shows some pictures, some examples for local buckling. So look at this one. In these shapes, only is buckle the flange buckles prior to the global failure, same as this one. And actually, typically HSS shapes have very thin walls, so they typically local buckling may control. Okay. And because of the local buckling, we define the member as a non-slender members or slender members. So if the width to thickness ratio for both of the flange and the webs are less than the limit, then we call it non-slender members. If the width is if one of the elements of your shape has a width to thickness ratio that is greater than the limit, then we call it slender members. Okay, so for example, you have a I shape or wide flange shape, right? So you check all the elements. You check the flange and check the web, and both of them, the width to thickness ratio of both of them are less than the limit. That means you're good. You don't have to worry about the local buckling. But if one of them, if only the flange width to thickness ratio exceed the limit, or the width to thickness ratio of the web exceed the limit, then we call it a slender members. That means local buckling may control. And the limit is listed in the table B4.1a. Okay, so check the limit from the table B4.1a. Okay, so let's take a look at it from the menu. So when we talk about chapter B, is referring to a chapter in part 16. So we find chapter 16, part 16, and look at the table of the content. We are looking for chapter B, and it says it's B4, right? It's B4. Okay, B4, find the B4 from your menu, and you find this table. Okay, table B4.1a, and next page you will see a table B4.1b. They look very similar. If you read the title, so table B4.1a is for compression member. It's the limit of width to thickness ratios for compression element member subjected to axial compression. So that we're going to use it for compression member design. And table B4.1b is for the compressive element members subjected to fracture. So it's actually for a beam. So check the local buckling for a beam for a fractal members. So in column design, we check table 4.18. Okay, so let's zoom in, we will see the limit with the thickness ratio limit. Okay, so for the I-shaped, for those shapes, the limit for flange is 0.56 times square root of E over Fy. And remember, look at the first column, unstiffened element. Unstiffened element is referring to the flanges, the flange. See, the flange is unstiffened element. And the next portion, the second portion of the table is for stiffened element. So for example, so case 5, so this limit is for the web. So the web of the I shape is a stiffened member, see, because it's restricted on both ends by the flanges, right? So a web is a stiffened member. So the limit for a web is 1.49 times square root of EFY ratio. Okay, so now you understand how to find the limits of width to thickness ratio for a flange and for a web. So we typically use this one for the flange limit and use this one for web limit. Okay. So with that being said, if you want to know if the member you want to choose is a slender member or a non-slender member, then you have to check the width to thickness ratio for the flange and the web. You have to go through a series of calculation, right? So to calculate the limit and find the width to thickness ratio from the table, from table 1. Alright, but there is a much easier way to figure out if local buckling would be controlling. Is if the shape has Fy of 50 ksi. Okay, so let's look at the table 1 first. Okay, so let's just randomly find a page for in the table 1-1. Okay, and you will see some members have superscript. Some of them have a superscript of C. Some of them have superscript of H, and some of them have V or F. And the footnote explains that. So the superscript C means the shape is slender for compression with Fy of 50 ksi. Okay. So that means if you choose to use steel A992, that means your Fy is 50 ksi. Then you just look at it, find this member in table 1-1 to see if there is no superscripts on it. So if there is no superscript of C on that shape, means with Fy equals 50 ksi, this shape is slender. This shape is slender means either the width to thickness ratio of the flange exceed the limit, or the width to thickness ratio of the web exceed the limit. Okay, so for some other members, there is no any superscriptions on it, means with Fy equals 50 ksi, this member is non-slender. This is non-slender for compression. Okay, and it's compact for a fractal member. We can talk about it later. Right. So we would try to select a member without the superscript. Okay, so that way we don't have to worry about the local buckling. Okay, let's continue. So especially in the textbook, a lot of problems like this, right? You have an analysis model like this, and oftentimes you see in the job site, right here, you want to know what model I should use, how to determine the compressive strength, VPN, for that element, right? So let's look at it. Let's take a look at the column highlighted in the picture. So at the top joint, we see there's a beam bolted into the column, providing a bracing for this column. And in the plan of the page, on the page, then you will see it's braced on the top joint and on the intermediate joint. Okay, so at the plane perpendicular to the page, it is only braced at the top, as shown here. So we call it it's braced about x-axis. So that means if you take an aerial view of this column, it's actually braced on the flange. It's braced on the flange, and this bracing preventing the column from bending about x-axis. X-axis usually for this column, bending about x-axis is harder than bending about y-axis, right? You can play with a beam like this. You will find that it's much harder to bend about the x-axis because it's stronger about the x-axis. So we call it braced at x-axis. So it's preventing buckling about the x-axis. And on the other hand, if you look on the plan of the page, it's buckled on the top and at the intermediate joint, about at web. So an aerial view shows that it's braced in between the web, in the middle of the web. So it's braced at here. So this bracing prevents the column bending about y-axis. So y is weak axis. So y is weak axis because it takes less force to bend about it. And the x-axis we call the strong axis. So from here you will see that the column may have different capacity in the different axes, about different axes, right? And if you read example 4.2, okay, so I suggest you to study example 4.2 in your textbook. Okay, example 4.2 in your textbook. It gives you a simple scenario because this column is only braced on the top. So if there's only one bracing on the column and it's braced on the top, then it will buckle about its weak axis. It will buckle about its weak axis. So say it will buckle right. It will buckle about its weak axis, right? Because it take less effort to buckle about y-axis, so it will buckle about y-axis. However, if you look at this problem, things becomes more complicated because you will have different effective lengths about x-axis and y-axis. Okay, so let's summarize the conditions we have in the problem statement. Okay, so in the problem, we know that the shape, we have the shape of W10 by 33, and it's made of A9I2. So if you look at the table 2-4, you will find that your Fy is actually equals to 50 KSI. Okay, so that's what we like. And it's braced at the truss joint in the member of y-axis and the x-axis, y-axis. Okay. And PU is 300 kips. 300 kips. It asks if the member is adequate, so it's actually asked for phi Pn. So we want to determine phi Pn and compare it with Pu. So if phi Pn is less than, is greater than Pu, then the design is adequate. Okay, so like I said, first of all, we want to determine if it is a non-slender member, right? So we have to check the local buckling first. Well, how to check the local buckling? So I just tell you that just look at, because Fy is equal to 50 KSI. So what I should do is just check the superscript in table 1-1. Okay, so please pause this video and then find this shape in table 1-1 and come back. Okay, we'll come back, and I believe you already found this shape in table 1-1, and I find there's no superscript for this shape. So that means local buckling will not control. So I don't have to worry about local buckling. Okay, so to prove that, you find page 1-20A and find the shape 10 by 33, no superscript, right? So it's a non-slender shape. If you look at this one, 10 by 22, it is a slender shape, so you have to so local buckling may control, so you have to check local buckling. You have to check VPN based on local buckling. So it's just gonna take more steps to get your VPN. Okay, so this one we don't have superscript, then local buckling will not be controlling. So what we're gonna do is to find VPN for the local buckling. Okay. Then let's go ahead to check global buckling. Okay, so check. And from table 1.1, we can find the basic shape properties. We can find that the gross cross-sectional area is 9.71, and then radius of gyration about the x-axis is 4.19, and Ry is 1.94. Okay, so find all this from table 1.1. Okay, now we're gonna go ahead to use the slides number 5. Okay, so use the number 5 to find out FCR and VPN. So the next step is find VPN. Okay, so like I said, so if we look at the x-axis buckling, x-axis buckling, strong axis buckling, right? So in this plan, there is only one bracing, so it's pinned at the top end and fixed end at the base. And under the load PU, it will buckle, so the buckled shape will be like that, right? And we learned about the equivalent. Effective length. So the equivalent effective length is the pin length. Is 0.8, so 0.8 L. So if you look at the table C-A-71 at page 16.1-570, you'll find the effective length factor. Okay, so there you go. Once we find this table, so we are case B, right? So for XX bending, we are case B. It's pinned at the top end and fixed at the base, and the design K value is 0.8. Although the theoretical K value is 0.7, so it means theoretically the pin and the distance from the pin and to the point of inflection is about 0.7 times L. But for the design, we're going to adapt 0.8. And when we look at the y-axis, so y-axis oriented this way, so the web is in the middle. So it's braced on the web, and it's preventing the buckling about y-axis. So the buckling shape is like this. And in this plan, there are two spans. One is 10 feet long, another one is 12 feet long, right? And for the first band is pin-pin connected. It's pin-pin connected. So for the first band, K is 1, and for the second span is fixed pin connected, so it's 0.8. Okay. And there are 3 scenarios. We really don't know which scenario will be controlling, so we have to look at it up. So based off what we learned so far, we know that the FCR, the critical stress, right? So VPN is equal to 0.9 times FCR times AG. And AG is the constant, so the VPN is related to FCR, and FCR is related to slenderness ratio. Right, slenderness ratio, KL over R, and the middle one is 4.7 over E, FY ratio. Okay, so we can see the larger slenderness ratio is, the lesser FCR is, right? So we can see here the 3 scenarios, the larger the slenderness ratio will be controlling. Okay, so we want to list it. Axis and length in feet, and the K factor, and then radius of gyration is different for the different bending planes, and KL, slenderness ratio, KL over R. Okay, so let's look at the first scenario is bending about x-axis, so it's pinned on the end, so the total length is so the total length of this scenario is 22, right? It's 22, and the K factor is 0.8. Okay, so radius for gyration, so it's gamma Rx is 0.19, right? So we determined it here, Rx. So we calculate KL over R. Remember to convert it to feet. Okay, so let's write it here. The first one is XX. KL over R about x-axis is 0.8 times the length, 22 feet, converted to inches. Okay, converted to inches because the radius of gyration is in inches, so it's inch, and divided by 4.19, and I get 50.4. Okay, so I get 54.4. It's the unitless. Okay, so that's the first scenario, and the second scenario is the first band for y-axis, right? Y-axis first band. We have 2 spans bending about the y-axis. So first band is 10 feet long, and the second is 12. Okay, so first band pin connected, K is equal to 1, and the second span pin fixed, so it's still 0.8. Okay, and the radius for gyration we determined to be 1.94 and 1.94 from the table 1.1, and give the calculation, and you will get the corresponding slenderness ratio, 61.9 and 59.4. Okay, so if you look at the curve, you'll see that the larger slenderness ratio will yield smaller FCR and then the smaller VPN. So the largest the KL over R will be controlling. So I will say this one will be controlling. Okay, so I'm gonna determine VPN based off 61.9, based off the largest, the slenderness ratio. Okay. It's worth to mention that there are actually 3 methods to find VPN. So let's talk about it one by one. Okay. So there are 3 methods to determine VPN. Alright, let's look at method 1. Method 1 is the most general one. We're just going to use the general equation in the menu 3-2 to 3-4. Okay, and so 4.71 times E over Fy, okay, equals 4.71, and E is 29,050, right? 50 KSI. So it's equal to 113. So the controlling slenderness ratio is 61.9, so it's in the inelastic region. So we're going to use the first equation. So we're going to use this equation, FCR, use this equation. Okay, so your FCR is 0.65a to the power of Fy over Fe times Fy. So here we have to calculate Fe first, and your Fe is pi square E over slenderness ratio squared. Okay, so it's equal to pi squared 29,061.9 squared, and got 74.7 KSI. Okay. And plug that in. FCR is 0.65a to the power of 50 over 74.7 times 50 KSI. Okay, and I get 37.8 KSI. Okay. And elastic control, inelastic controls, right? Inelastic controls. are here. So inelastic controls. So your phi Pn is equal to 0.9 FCR times Ag. So it's equal to 0.9 times 37.8 KSI times 9.71 inch squared. Is equal to 330 kips, right? And you're gonna compare it with your PU. PU is 300, so we're good. Okay, so that's the method one. It's we use the general equation, so it is applicable for any shapes, for any kind of shapes. It applies to I shape, HSS, any shape, any kind of a shape, right? As long as you can find your FE, FY, and the slenderness ratio. So it's a very general method. Okay, and the second method is to use the table in part 4. Okay. Use table 4-1 in your menu. In steel menu. All right. Okay. So let's find that first. Let's find it first. If you find the table 4-1 in the steel menu, you will find that there are several yield stress. There are tables for different yield stress available. So there are tables for Fy equals 50 KSI, and there are tables for Fy equals to 65, and 70 KSI. So make sure you are using the right table, okay? And table 4-1 is based on weak axis buckling. Okay, so that's very important. So table 4-1 is based on weak axis buckling. So that means you're going to enter KL over R about YY axis and then find VPN. Okay. So let's take a look at the table. Okay, so we found the table. So this is the table include the shape we are looking for, 10×33, which is good. Okay, let's take a closer look. So it gives you VPN for various shapes. Okay, and you enter effective length LC. So you enter LC. Remember, effective length LC is equal to KL. So you enter KL about weak axis, so effective length with respect to least radius of gyration, RY. So this is based off. So this table is based on weak axis buckling. So it's assuming that weak axis controls. So you're gonna enter KLY and get VPN from that. Sounds pretty good, right? Sounds pretty daunting. But you may ask, what if my case is x-axis control? If my case is strong axis control, how can I still use table 4-1? the answer is yes, but we have to play a trick. Okay, so if KL are X controls, you cannot directly enter KLX into it, but you can play a trick like that. So let's take a look at it, the expression KL about x-axis. So what is KL about x-axis? So this is what we in this example, right? So bending about x-axis, so my KL is point A times the length, right? So this is what, so our KLX is 22 times point A, right? So for the first bend, y-axis bending, my KLY is 10 times 1, and for the second span, 12 feet, is 12 times point A. Okay, so KL over Rx can be rewritten in this way. So I can write it as KL x over Rx times Ry over Ry. Now I can look the numerator, look at this one as my equivalent KLY. So we call it KLY equivalent. Okay, so I define my equivalent KLY as KL x over Rx over Ry. We'll just move Ry to the denominator. All right. So then we back to the problem. Then if I want to find VPN based off the strong axis buckling, then I have to enter. Then I enter my equivalent KLY to find VPN. So enter equivalent Y to find VPN for strong axis buckling. Okay, and then back to this problem, we know that the controlling slenderness ratio is about weak axis buckling. So we, from the analysis from the table here, we can predict that the buckling will occur in the first span about y axis. So back to the problem. Okay, so back to the example. The controlling KLY is 61.9 feet. So what I'm going to do is to enter, oh sorry, not 61, the slenderness ratio is 10 feet. So I'm going to enter 10 feet into table 4.1. Okay, so find the shape 10 by 33 and enter 10 right here. And here we find VPN to be 330. Very simple. Okay, so here from the table we directly find VPN to be 330 kips. Right, and we find that is the same as we calculated based on the general equations, but it's so much easier, right? You may say, oh, I like the table 4-1 so much, can I always use 4-1? The answer is no, because not all the shapes are included in 4-1. So if you are calculating the shape not included in table 4-1, you have to use another method. Okay, and then next I'm gonna talk about the next method. Okay, so let's add one more page. Okay. Now there is another method included in part 4. There's another table we can use. So method 3, we can use table 4-14. Table 4-14. Okay, so let's take a look at table 4-14. Okay, so table 4-14 is at page 4-229. It gives a table the relationship between the Fy and the slenderness ratio LC over R. Again, LC is equal to KL. So in this table, if you know Fy, then enter your slenderness ratio and you find your phi FCR, your phi times critical stress. Okay. So in this example, my KL over my controlling slenderness ratio is 61.9, right? So remember. Okay. Then in this table is you find phi FCR from slenderness ratio. Slenderness ratio is KL over R, right? KL is LC. Okay. So in this problem, the controlling KL over R is 61.9. Let's just round up to 62. Okay. And then Fy is 50 KSI. Okay, and then we enter that, take a pause of this video, find the phi FCR from the table, from table 4-14. Okay, so enter 62. That's probably gonna in the next page. Okay, so enter 62. Fy 50 is gonna be right here. Enter 62. So I'll find my phi FCR to be 34. It's equal to 34 with a unit of KSI, right? And then use the general equation. Phi Pn equals phi FCR times Ag. So I got my phi FCR 34 KSI times Ag 9.71 inch squared. And I also get 330 KSI. Okay. So the nice thing about table 4-14 is not related to the shapes. So it's good for all the shapes. It's only related to your slenderness ratio and Fy. So as long as you know the slenderness ratio, the controlling slenderness ratio, and Fy, and you get phi FCR. Okay, so using the 3 different methods, we come across the same result. So pick any one of those as you like. Okay. All right. So thank you for watching. Thank you. Goodbye.